Let's play, is it a vector space? So here's a set V of vectors, and they're points in the plane whose second coordinate is 0. So this says V is the set that contains all points whose first coordinate is some real number, so X is a member of the reals, and the second coordinate is 0, some elements of V. We'd have like 2, 0, and negative 3, 0, and pi 0, and negative e 0, and so on. So we want to know if this set is a vector space just under the usual addition and scalar multiplication. So if you do, say, these two added together, 2, 0, plus negative 3, 0, you'd get 2 plus a negative 3 as your first coordinate, and 0 plus 0 is your second coordinate, so it'd be negative 1 and 0. And same thing with standard scalar multiplication. If you wanted to multiply 2, 0 times negative 3, you'd get negative 3 times 2 is negative 6, and negative 3 times 0 is 0. So just under the standard operations, is this a vector space? So we need to know if this set and the standard operations satisfy all of the vector space axioms. And here's a little bit of like a cheat sheet for the vector space axioms. So first we need to know, is this thing closed? Is this set closed under addition? So if I take two things in that set, do I get another thing in that set? And the answer is, it is closed, because if you take, say, x0 plus y0, you add those two things together, you get a real number plus a real number is a real number, and then 0 plus 0 is 0. So you're always going to get a real number for your first element and a 0 for your second element. So it is closed under addition. And that's because the reals are, it's hard to get bumped out of the real numbers. And then can you change the order here of, if you do x0 plus y0, is that equal to y0 plus x0? And that's a question mark. And it is, because this is going to be xy comma 0, this is going to be yx comma 0, and x and y are real numbers, so this axiom is good. This is good. 3 is also satisfied. If you were to add x0 plus y0, and then add to that another vector, say z0, you'd get, then your first entry, you'd get x plus y, and then plus a z0, and since the real numbers are associative, this is going to inherit this associativity. So this is going to be x0, plus y0 plus z0. So that's satisfied. And the fourth is satisfied also, because 0, 0 is in there, because in order to be in V, all you have to do is have a second coordinate of 0, so you're all set there. This is good. That's in V, so that's good. So we have an additive identity. An additive inverse, if you take x0 and you add that to negative x0, this is in V because it satisfies the conditions to be in V. This is a real number, this is 0, and when you add this together you get the additive identity. So the inverses are there. It is also closed under scalar multiplication, so that's number 6. If you take a real number, k, and you multiply it by x0, like we did up here with k equals negative 3 and x0 being 2, 0, you're going to get kx0. K is a real number, x is a real number, so k times x is a real number, so this is closed under scalar multiplication. The next three axioms are essentially inherited by the properties of real numbers, because if you did k times x0 plus y0, in here you'd get the vector x plus y comma 0, and then you get k times x plus y. K times quantity x plus y is your first entry, which would be kx plus ky, because that distributive log gets inherited from the real numbers. So this is going to be k times x0 plus k times y0, and you can verify that step by step. I'm not doing a proof here, just sort of verifying that this does in fact work. And similarly for the 8th axiom here, whether you do the scalar multiplication first or excuse me, the addition of the two scalars first and then do the multiplication, or do the scalar multiplication here first and then do the addition. You get the same thing. So here you could distribute this k plus l in there, and you get k plus l times quantity k plus l times your first coordinate x, and then you distribute and then undo, and you could get to there. So this works. And same thing here, if you multiply k times l times x is 0, that's going to be k times l times x 0, and you can verify that fairly simply algebraically. And then one time, if you take and multiply 1 times any vector in there, you're going to get 1 times x is x 0, so that's satisfied. So all 10 axioms of the definition of a vector space are satisfied here. So the answer, is this a vector space? Yes, it is. And we can verify that, not to say prove it. Let's look at another one. So here's another set of vectors. V is equal to the vectors ordered pairs x and y, but in this case x and y are from the integers. So the integers are, if you draw a number line, 0, 1, 2, 3, negative 1, negative 2, negative 3. If you draw a number line, typically your tick marks represent the integers, and mine do here. So the integers are 0, and then what some people call the counting numbers, 1, 2, 3, and then the negative, those also, negative 1, negative 2, negative 3, going on forever in both directions. So we want to know whether this set, again under the usual operations, the standard operations, so if you were to add, like, say 1, 2 plus 3, 4, that would be 1 plus 3 is 4, and 2 plus 4 is 6, or if you did 5 times 1, 2, you'd get 5, 10. So again, the standard operations here, same as the previous example, but now in order to be in V, the two entries in that ordered pair have to be from the integers. So we want to look at this and see if this is a vector space. Are all of these axioms satisfied? And the answer is no. This is not a vector space. And the problem in this case, or at least one problem that I see right away that jumps out at me, is that it is not closed under scalar multiplication. So axiom 6 is no good in this case. Because if you were to take, say, k equals 1/2, so our scalars always come from the real numbers. And that's the problem with this set. That's why it's not a vector space, is because these integers easily get booted out of the integers. It's not easy to get booted out of the real numbers. The real numbers is the entire line, everything on the line, so it's hard to get pushed off that line, but it is certainly hard to get pushed out of those tick marks. So if you take k times, k is 1, 2, and you multiply it, say, times, say 3, 2, you'd get 1/2. 3, 2, which is 3/2, and 1. This is not in V. So all you need is one axiom to be no good, and you're not a vector space. So this is not a vector space. The integers are not tremendously well behaved for vector spaces. Okay, another example. So in this case, V is the set of polynomials of degree 2 with real coefficients under the standard operations. So let's just get a feel for this set first. So we need a polynomial of degree 2, so we would need, I'm going to work with the variable x, so we need to have an x squared. So that's in our set. X squared minus 3x plus 2. That's in our set. That's a polynomial of degree 2. This 3x plus 5. This would not be in that set because it's not degree 2, it's degree 1, unless I put a squared on there, and then it is in there. So we have things that look like this, that are polynomials of degree 2, no higher and no lower. And if we add these things together, so if we wanted to do like this one plus this one, so x squared plus x squared minus 3x plus 2, so the standard operation, you just combine like terms. So you'd get equals 2x squared minus 3x plus 2. And if you wanted to multiply one, like say we wanted to multiply 5 times x squared minus 3x plus 2. Still, the scalar multiplication just works under the distributive law. So we want to know if this is a vector space under the standard operations. So here again, as my little cheat sheet for all the axioms in order to be a vector space, you can pause here and think about this for a minute before I give it away. This is not a vector space, and there are some problems with this right from the get-go. Axiom 1 is no good because you have x squared, negative x squared is in this set because it's a polynomial of degree 2. X squared is in there, so if I take negative x squared and I add x squared, I get 0. So I bumped myself out of that set, so it's not closed under addition. This one's okay, this one's okay. Axiom 4 also. The 0 vector, which would just be the number 0, is not in that set because it's not degree 2, it's degree 0, so that's no good. The additive inverse, I think, is okay. It's closed under scalar multiplication, that's true. I think the scalar multiplication and all that is okay. So you have 2 axioms here at least that are no good, that this thing violates. So you only need one. I mean, if you violate one axiom, then you're not a vector space anymore. So I didn't have to come up with 2 examples, just the one counterexample. Okay. Now this one here, P sub 2, is standard notation for the set of polynomials of degree 2 or less with real coefficients under the standard operations. Is this a vector space? Again, here are the axioms under the definition of a vector space. This one is a vector space. I'm going to say yes. It is a vector space. The 2 problems that we saw with the previous example with polynomials of degree exactly 2 were that it was not closed under addition because we had the negative x squared plus the x squared gets you 0, which bumped you out of that set. But this is polynomials of degree 2 or less. So now when you do x squared plus a negative x squared and you get 0, this is in P2 because it is a polynomial of degree 2 or less. In this case it happens to be less. And same thing with the 0 vector being in that set. It is in that set because it's degree 2 or less. So this is a vector space, and I'll leave it as an exercise to go and check each of those axioms individually, and this is what your homework will look like. Your homework today will be, let's play, is it a vector space? Okay, very good.